Okay, in this final equilibrium lesson, we're going to learn how to predict whether a precipitate will form if you mix solutions together. Now, this is related to some of the solubility rules that you learned in the last unit, and it's definitely going to use a lot of the previous lessons that we talked about in this unit. So, first and foremost, reminder, whenever you're working with precipitation, this is solubility equilibrium. And solubility equilibrium is always an equation written with the solid on the left-hand side, that's your reactant side, and your products, which are dissolved, those are on your right-hand side. All right, so we will be constantly referring to left and right. Okay, left also means backwards, right means forwards. All right, so we'll be referring to that a lot. Okay, so mathematically, we know that we can write the equilibrium expression, KEQ, and we know that when we do that, it's products over reactants, and that you only use equilibrium concentrations. So, EQ. Now, that's what the concentrations will be once equilibrium is established. But when you have initial concentrations, what we set up is not KEQ, it is Q. And remember, the difference is that Q uses initial concentrations. So in order to predict whether a reaction is going to precipitate or not, that implies the reaction has not yet gotten to equilibrium. Therefore, these calculations are all Q calculations. So in order to determine this, or to interpret this, when the value of Q that you calculate is less than K, what that's basically telling you is that you don't have enough product. So if you don't have enough product, the system's going to make more product. It's going to shift to the right. Now, if it shifts to the right, all of your products on the right side are ions, so you will see no solids. No solids form. No precipitate. If Q is greater than KSP, well, the opposite is true. Now you have too much product, which means you have to get rid of some. The reaction is going to shift to the left, and if it shifts to the left, remember how our solids are on the left side, we will see solids form, and that's our precipitate. Okay, so let's try our first example. So here we have silver ion and we have chromate. So this is the equilibrium for the solid compound silver chromate. So Ag2CrO4 solid, and we will get 2 silver ions, and we will get the chromate ion. The Q for this would be the concentration of silver squared times the concentration of chromate. And of course, these are initial concentrations. Now, in this problem, we are told what the initial concentrations are. They're both 0.001 molar. So if we substitute those in, we get a value of 1 times 10 to the minus 9. That's our Q value. That value is definitely greater than the given K, which is 2 times 10 to the negative 12. So what does that mean? If we have too much product, this reaction will have to go backwards, and if it goes backwards, we see solids form. We see this precipitate. So what we did here is we solved for Q, and then we compared Q to the value of K. All right, let's try another one. So this next, that was more of a beginner type of problem. This is more of a realistic type of problem now. So if we mix potassium chromate with silver nitrate, so here we are mixing two different solutions together. Imagine taking two test tubes and pouring them both into a beaker. We want to know if we see a precipitate form. But in order to know that, we need to solve for Q, and in order to solve for Q, we need to solve for the concentrations. So it helps to remember that molarity, which is the moles of the solute over the liter of the solution, we can rearrange this, and this is how we're going to find moles. We're doing this because we are given the volume and we're given the molarity for each of these. So for the first reactant, we're going to take the molarity, 6.8 times 10 to the minus 4, and multiply it by its volume, 0.05. Let's go ahead and crunch that. So that's 3.4 times 10 to the negative 5th moles of potassium chromate. Now, in our solubility equilibrium equation for silver chromate, it was chromate, not potassium chromate. Let me rewrite the equation here since it's off the screen. So we have to use the proper units, which means for every potassium chromate, there is one chromate in it. So that means we have 3.4 times 10 to the minus 5th moles of just chromate. Okay, those are our moles. Let's do the other reactant. $50 milliliters, and well, actually we'll start with molarity, 9.6 times 10 to the minus 5th molar. Fix that. Minus 5th. The volume is also 50 milliliters. So here we get 4.8 times 10 to the minus 6th. And that's moles of silver nitrate. Okay, so now again, it's not silver nitrate we need, it's just the silver. So for every silver nitrate, there is one silver ion. So we have 4.8 times 10 to the minus 6 moles of silver. Okay, so those are the moles. But in order to do Q, we need molarities. So molarity is moles over volume, and our total volume is 100 because we added 50 milliliters plus 50 milliliters. So we divide the moles, each of these moles, by 0.1 liters. So what that turns out to be then is 3.4 times 10 to the negative 4th molar for the chromate, 4.8 times 10 to the minus 5th molar for the silver. And now we solve for Q. Q is the silver concentration squared times the chromate concentration. We have both of these values. We plug them in and we solve. So let's see what we get. All right, Q is equal to 5.5 times 10 to the minus 12. And nope, no, it's not. I misentered that. Let me recalculate that again. 4.8 times 10 to the negative fifth. Square that times 3.4 times 10 to the negative fourth. Okay, Q is equal to 7.8 times 10 to the minus 13. And that is less than KSP, because if you recall, KSP was 2 times 10 to the negative 12. So what that means is there is not enough product. The reaction will shift forward to the right, and if it goes to the right, then we do not see any solids. No precipitate. Okay. So what did we do here? We wrote the equation. We solved for the moles of each of the reactants, and then we divided by what the total volume was to find the molarity of each reactant. And then we plugged them into Q, came up with a number, and then we compared that Q number to K. That told us which direction this reaction was going to shift, and because it shifted to the right, we do not see solids form. No precipitate. Okay, so now let's talk about what if there is a common ion. A common ion is whenever you're trying to dissolve something, but one of the parts of the compound is already present. So in this situation here, in this first example, we've got a 0.1 molar solution of HCl. If it's 0.1 molar HCl, what that means is it's 0.1 molar H plus and 0.1 molar Cl minus. And we're trying to dissolve lead chloride. So when we try to dissolve lead chloride, there's already chloride there, which means you're not going to be able to dissolve as much. If we look at this from an ice table perspective, remember that we don't enter any values underneath the solid. That's why there's a big X. Okay. We want to figure out what the solubility is. So the solubility here, well, we start with no lead present in solution, and we do start with 0.1 molar for the chloride. We always add to the side that has a 0. And we're adding 2x to the chlorides because of the coefficient. All right, so that's our ice table. So to solve for the solubility, we use the KSP value, which I don't remember off the top of my head. I need to look that up real quick. It was in a previous lesson, but it's not on this page. KSP, lead chloride. Okay, so the KSP for lead chloride is 1.6 times 10 to the negative fifth. All right, so our equilibrium expression is going to be the KSP is equal to the products or the reactants, which would be quantity X times quantity 0.1 plus 2X, and the chloride will be squared. So X is the solubility. Let's go ahead and solve for that. Okay, so the value of X is 0.0015. So that's the solubility. The solubility when there is a common ion. The common ion here is chloride. Now, we did this solubility in an earlier problem in a previous lesson, And the PbCl2 solubility in plain water, meaning there was no common ion, was 0.016. So this is considered as normal solubility, but now in a common ion, it's less. And how much less it's going to be depends on how much of it is present to begin with. So the point is, common ions lower the solubility. They lower how much you can dissolve because there's some already there. All right. So let's try this next one. KSP for silver. Oh, you know, this is a different value than earlier. We said it was 2. Okay, so silver chromate. Same equation as before. KSP expression. What is its solubility? All right, well, we're going to have 2x for silver and x for chromate because there's twice as much silver ion as chromate. So what that means then is the 2 times 10 to the minus 12 is equal to quantity 2x, close quantity squared, times x. X is our solubility. Let's solve for that. X is 7.9 times 10 to the minus 5th. So this is what would be considered as normal solubility. Now that's molarity, of course. Okay, so the normal solubility, the molarity, is 7.9 times 10 to the negative 5th. So now let's do this when there's a common ion present. So we write ourselves an equation again, and they're saying that we are dissolving this in 0.005 molar silver nitrate solution. So right here, 0.005, that is our initial concentration for silver. The change rho is the same as it would be. So we have our equilibrium rho filled out. Let's go ahead and plug it into the KSP expression. Oops. Now let's solve for x. Okay, so x is now 8.0 times 10 to the negative 8th molar. So this is the solubility with a common ion. Note the difference. The solubility has changed drastically. We had a common ion present, and now it's significantly lower. And that's the point. Common ions lower the solubility. Okay, so the last problem is going to be application, actually the last 2 problems, of everything we just talked about. So try this first problem here, then pause it, and then I'll go through and solve it. Likewise with the next one. Okay. So here, silver nitrate, sodium chromate, and we have these values our compound of interest is going to be the silver chromate again, like it was before, because sodium nitrate is soluble, so it can't be that one. So again, our equation will be this. Okay, we need to calculate the molarities. So for the first, 0.0025 molar times 0.025 liters (6.25 times 10 to the minus fifth), and that's moles of silver nitrate. Now, of course, it's not silver nitrate that we need, it's just the silver. All right, let's do the other. So 0.0015 molar times 0.025 liters. (3.75 times 10 to the minus fifth moles), and that's of sodium chromate. And there's 1 chromate for every sodium chromate. These 5s look like 6s sometimes. Okay, so we have moles of both reactants. I need to find the molarities, so I need to divide them both by what the total volume is. 25 plus 25 is 50, so each of these divided by 0.05 liters will give me the molarity. So this one, 7.5 times 10 to the minus 4 molar. And 1.25 times 10 to the minus 3 molar. Okay, let's solve for Q. Let's go ahead and substitute. This goes into here. This goes into here. So our value for Q is 1.2 times 10 to the negative 9th. And that is greater than the KSP. If you recall, the KSP was 2 times 10 to the negative 12th. So that means this reaction, there's too much product, this reaction will go backwards, and yes, a precipitate forms. Okay. And let's do the last example again. Go ahead and pause it and try to work it out yourself, and then I'll go over it. Okay, so what do we have here? We've got calcium nitrate and sodium fluoride. Well, I know that sodium nitrate is soluble, so it's not going to be those. So really what we're interested in here is calcium and fluoride. So our equation will be the solubility equilibrium for calcium fluoride. like so. The KSP value here is given, and we'll be able to compare it. All right, so let's find our concentrations. So for the sodium fluoride, 0.0020 molar times 0.002 liters, because 2 milliliters is 0.002 liters, is going to be 4 times 10 to the negative 6 moles of NaF, but of course it's just the F that we're after. Let's do the other one. 0.005 molar times 0.001 liters. So 5 times 10 to the negative 6th moles of calcium nitrates. We're only interested in the calcium. So 5 times 10 to the negative 6 moles of calcium. All right, so we have our moles for both. In order to solve for Q, we need molarities. So our total volume of our solution here is 3 milliliters, which is pretty small. Divide each of these by 0.003 liters. So fluoride is 0.00133, repeating, molar. The calcium .0016, repeating, molar. Okay, let's set up our Q expression. Q is going to be equal to the concentration of the calcium initial times the concentration of the fluoride initial squared. We have our calcium to be 0.0016, repeating. We have our fluoride to be 0.0013, repeating. So let's see what we get. Q is 3.0 times 10 to the negative 9th. Which is greater than KSP, because here's KSP. So this reaction goes backwards, and yes, a precipitate forms.